All right, let's look at the transient response in a capacitive circuit. The placement of charge on the plates of a capacitor does not happen instantaneously. In other words, if I look at this capacitor, I'd like to charge it up to this resistor. You have a switch and you close the switch. Let's say I have a 12-volt source. The voltage across the capacitor is going to build up exponentially. If I look at this, the voltage is actually, you have placing the charge in the plates, and placing the charges is not happen instantly. It's very similar. Every time you have a dynamic systems, the instantaneous value of whatever the output might be. A very simple example would be if you're driving a vehicle and this is the speed that you want to reach, the speed of, let's say, 70 miles an hour. You cannot go from 0 to 70 miles in 0 seconds. That will require infinite amount of torque, and you got to buy a set of tires just about every day. There are some physical limitations in anything that is dynamic. As far as the capacitors, is the first order system. Well, by that I mean if you have one storage elements in a system, the system becomes first order, which means the differential equation would be a first order differential equation describing the dynamic of that system. We're going to see later in this chapter that the capacitor actually does differentiate the voltage waveform. So the current I sub C will be some function of the rate of change of the voltage with respect to time across the capacitance. If the capacitance voltage does not change, it stays constant, there will be no current flowing. But once we're going to put another storage element, such as an inductor that we're going to discuss in the next chapter, the system becomes second order. The second order system could oscillate up and down and no settle downs. But all first order system, fortunately, they behave exponentially, just like you have it in here. This is called a transient response. So everything that is function of time, it will have a transient response and then will reach a steady state response. And for the capacitive circuit, the transient response is an exponential function. As I said earlier, all first order system, they behave exponentially. If the voltage from 0, let's say you want to charge up this capacitance, and for the voltage to go from 0 to 12 volts instantly, like a step, then you need to have infinite amount of current flow. And again, there's no such a system, some kind of a power source that could put out a million ampere in 1 second, so it's just impossible. So it will behave exponentially, and we're going to look at how you come up with the equation for the system. At the same time, when the current is, when the voltage is building up, initially you have extremely high current, that's the maximum current, which is called current on rush. As soon as you close the switch, you have a very high current flowing initially, because the voltage across the cap cannot change instantly. So if the cap is completely discharged, it's going to stay at 0. So with that 12 volts, it's going to appear across the resistor instantly at time you close the switch, which is E divided by R. So you have a very high current flow. When capacitor is completely charged up, it acts like an open circuit. There's no more placement of charges. Where there's no more placement of charges, I mean the current is 0, so it does act like an open circuit. And that's what happened with the voltage. The voltage is building up. One time constant, it reaches 63%. We're going to talk about that. And then after 5 time constant, it will reach the steady state. By the same token, the current is going to be maximum initially, and then when the voltage as increases, the current to the cap is completely goes down to 0. And this is an exponential function. E to the minus x, when x is equal to 0, you get 1. When x is equal to 1, you get e to the minus 1, which is 1 over e. The number e is 2.71828. As an infinite number, I give you 0.3679. So that's what you see in this graph, that after 1 time constant, the current is already at 0.362. But the voltage is 1 minus, then if you take 1 minus 0.362, you give you 0.3862, you give you 0.632. So it's the exact opposite. And so forth. After 5 time constant, you see it's almost down to 0. So because of that, we assume the capacitor will charge up completely after 5 time constant. And so is the current. The current will almost down to 0 after 5 time constant. Now the factor tau, which is a time constant, is known as a time constant for the network, has the unit of time as shown below. If you look at the time constant, which is equal to, by definition, is R times C. R is the voltage divided by the current. Capacitance we define to be charges divided by the voltage. Well, the voltage and the voltage will cancel out. I is Q divided by T. Q will cancel out, so you end up with 1 over 1 over T is equal to T. So the time constant, and that's the reason they call it the time constant, which is the product of R times C, and that has a unit of time in seconds. So here's the voltage for the capacitor. And the voltage there's a way you can actually derive this equation. You can do it with a simple differential equations, but we're not going to get into that because you have not done the differential equation yet. So initially, if I let t is equal to 0, e to the minus 0 become 1, 1 minus 1 is 0. So the voltage is going to start at 0. As t approaches infinity, again, infinity is a relative term, which is 5 time constant. If I replace t with 5 tau, tau and tau will cancel out. You get e to the minus 5, which is almost 0.000 from this table. E to the minus 5 is 0.0067, so it's almost down to 0. So that's 0, so the voltage is going to charge up, the capacitor is going to charge up to the input voltage. So this is where the switching is happening, and this is after 5 time constant. The voltage is going to reach a steady state value. The smaller time constant, the faster the resistance, the capacitor is going to charge up. The shorter the time constant is. So there's two ways you can actually, two different components. It controls the time constant. How fast or how slow you want to charge up is actually controlled by the RC product. And the same thing for the current. Again, as I said, when you close the switch, you got to keep this in mind. Every time you have a capacitive circuit, if the cap is completely discharged initially, the voltage, as soon as you close the switch or you put some kind of a new excitation into the circuit, the voltage across the cap is going to stay at 0 at time t is equal to 0. So the voltage cannot change instantly, but the current to the capacitor could change instantly. We're going to see if I charge the capacitor and I switch to discharging it, then the current could go from positive down to a negative value. So initially the cap is completely discharged, this voltage is 0, then all the voltage is going to be across the resistor. So initially you have E divided by R. So that's the equation, E divided by R, e to the minus t over tau, to take care of that exponential function. So it started with E divided by R, the maximum after 5 time constant, which is 0.0067, which is 0.67% of the final value, so it goes down to 0. An electrical, they do 5 time constant. In a mechanical system, they usually look at the 4 time constant. Within 4 time constant, that's called 2% criteria. The output, it reaches within 98% of the final value. But electrical is very custom by IEEE, is defined to be 5 time constant. Now, when initially, when the cap is completely discharged, it acts like a short circuit. If completely charged up, it acts like an open circuit. Even though everything is still in place, there's a conductivity within, but remember the insulator between the two parallel plates is not conducting the current. Therefore, when it's completely charged up, you have no more displacement current due to the electric field. But so for when you do the analysis, you assume when the cap is completely charged up, it's going to act like an open circuit. When it's completed discharge, it acts like a short circuit. So initially, when the switch is closed, there is no initial current, there's no initial voltage in the cap. As soon as you close the switch, the capacitor is going to act like a short circuit, so the voltage is 0. When it's completely charged up, it will act like an open circuit. So initially, if there's no initial charge in the cap, and if you put a capacitor in the circuit If you want to make sure there's initially discharge, you just touch both leads together, and what that would do would instantly discharge the capacitance. So you put it in a circuit, and initially you get a maximum current flow, which is called current and rush, which is equal to the voltage divided by the resistance R that we discussed. So the current initially will be a maximum, and then we'll go down with this equation for the current. But the voltage across the resistor would be equal to whatever the current is multiplied by R. So it has the same format, the same exponential function. But the voltage across the capacitor would be 0 initially, but the voltage across the resistor could change instantly. As soon as you close the switch, there is no voltage across the resistor, but the voltage will go from 0 to E initially at time t is equal to 0. So the voltage across the resistor can change instantly. So is the current to the resistor. As the same thing is true with the current to the capacitor, but not the voltage across the capacitor. The voltage across the capacitor will start at 0, and it's going to go up, will grow exponentially to reach the steady state value. Let's look at an example. In this figure 34, you have 8 kilo resistor hooked up to the 4 microfarads. You close it to at time t is equal to 0, and then we assume if the voltage, initial voltage across the cap is not given, that means the cap is initially discharged. It says find the mathematical expression for the transient behavior for the voltage V sub C and the voltage V sub R when the switch is closed. Then we plot the voltage waveform for V sub C versus the time constant and versus the time as well for I sub C and voltage across the resistor. We want to calculate the value of V sub C at 20 milliseconds. So to do this, first thing you want to do is calculate the time constant for the circuit, so you get some feelings how long it's going to take for the cap to completely charged up. So the time constant is equal to R times C, tau. R has to be in ohms, C has to be in farads, then tau would be in seconds. 8 kilo is 32 times 4 times 10 to the 3 for K, and 10 to the minus 6 for micro. If you calculate that, it gives you 32 milliseconds. 3 of those will cancel out. That gives you 10 to the minus 3, which is milli. It gives you 32 milliseconds. 32 milliseconds. So the voltage V sub C is equal to E. This is a charging for the voltage. We're going to talk about a discharging. You have a different equation. So you're charging up the capacitors, E to the minus T over tau. Plug the values in. E is equal to 40. And tau is equal to 32 milliseconds. For the current, would be equal to 40 divided by 8K. Initially, again, this voltage is 0. All the voltage is going to appear across the resistor, which gives you a maximum current. 40 divided by 8K, that gives you 5 milliamps. And then all the voltage and the currents in the circuit that will have the same time constant. So be e to the minus t over 32 milliseconds. For the voltage R, initially is 40 volts. When t is equal to 0, it gives you 40 volts. When cap is completely charged up, it acts like an open circuit. There's no current flow, so the voltage will go down to 0 when the cap is completely charged up. So that's the voltage, the current, and the voltage across the resistor, voltage across the cap. Let's see what happens after 20 milliseconds. So you have the equation. So the voltage is going to start out with 0. It's going to reach 40 volts, but at 5 times time constant, which is 5 times 32, it's about 160 milliseconds. So they want you to plot it versus the time constant, also versus time. So after 160 milliseconds, that cap is completely charged up. At the 20 milliseconds, which is someplace right here, which is not even half of a time constant, at 20 milliseconds, you just plug in the equation for t is equal to 20 milliseconds. Millisecond will cancel out. 20 divided by 32 is 0.625. You calculate e to the minus 0.625, it gives you 0.53526. Multiply that by 40, it gives you 18.6 volts. So at t is equal to 20 milliseconds, the cap voltage is going to already gone up to 18.6 volts. Part D of the problem is asking when the charging phase has passed, how much charge is accumulated on the plates. again 5 time constant, the cap is completely charged up, and we want to calculate how much charges accumulate on a plate. 5 time constant is equal to 160 milliseconds, which is 0.16 seconds. So the charge is equal to capacitance times the voltage. You got 4 micro, and the voltage completely charged up to 40 volts. So you multiply 4 micro multiplied by 40. That gives you 160 microcoulombs. They want you to calculate or draw the plot, the waveform for the current I of C, and also the voltage V sub R, which is exactly identical. It started out with 5 milliamps. It goes down to 0 after 5 milliseconds. 5 time constant, which is 160 milliseconds. But the voltage would be whatever the current is, exact shape. You just multiply by 8K, and everything is just linear, which is at 40 volts. It goes down to 0. And part E of the problem, it says if the capacitor has a leakage resistance of 10,000 megaohms, what is an initial current, leakage current, and once the capacitor is separated from the circuit, so you put it on the shelf, then how long does it take to totally discharge because of due to the leakage current? Well, you have 40 volts completely charged up. Remember, we look at the model, the parallel model. So 40 divided by the resistance for the R sub P for the model for the capacitance. That gives you 4 nanoamps. That's how much leakage current you're going to have. So once you take it off from the circuit and again put it on the shelf, then you got 4 nanoamps is going to go to the capacitance. It's a discharge, a leakage. To want to calculate how long it's going to take to complete a discharge, you calculate the value of T is Q divided by I. You have 160 microcoulomb accumulated. Divide that by the 4 nanoamps. Make sure this is in coulomb, this is in amp, so that would be 10 to the minus 6. Nano is 10 to the minus 9. If you calculate that, it gives you 40,000 seconds. And if you divide that by 3,600 to calculate in terms of hours, it gives you about 11.1111 hours. That's how long it's going to take for the cap to complete a discharge once you take it out of the circuit. All right, let's look at the discharging phase. We want to look at how the discharge capacitor will exert some controls and how long the discharge time will be. You can, of course, place a lead directly across the capacitor I discussed, we mentioned earlier, to discharge it very quickly. And possibly you can see some kind of a visual spark. Depends how much charges you have, what type of a capacitor. If it's a big capacitor, you definitely see the spark. But for large capacitors, such as the one in TV or the motors, this should be not attempted because of high voltage involved, unless, of course, you're trained how to handle that kind of a high voltage and high charges. Now, if you position 1 for this circuit, the cap is completely charged up, and then after 5 time constant, you switch from position 1 to 2. Let's look at the current direction. Of course, when this voltage source is in, the current is flowing from left to right and charging up the capacitors. But as soon as you switch to position 2, the cap now acts like a constant voltage source. In fact, when the people they do transient with a capacitive circuits in it, right after the switching, they put a voltage source in there, whatever that capacitor is already charged up to. So it does like a source now. So the current will change direction immediately, instantly. It goes from right to left. And so, but that's possible. The current to the capacitor could change instantly, but not the voltage. So part A is the charging, and part picture B is the discharging configuration. Now when it discharges, the voltage starts at a maximum, and then will go down to 0. So discharging, the equation you do not have the parenthesis 1 minus e to the minus t over t. The equation for the voltage during the discharging cycle is the same as the current due to the charging cycle. So they're going to start out the current will start out e to the r, that's for the charging. This is position 1. Let's say after 5 time constant, you switch to position 2. So the cap is completely charged up. Now it's going to discharge. After 5 time constant is completely discharged, if you're switching back to position 1 again, you're going to charge it up. And you can actually do this in a lab, put in some kind of a square wave, which is positive and negative. During a positive cycle, the cap is charging up. When the voltage is dropping to negative, it will discharge it. Or you can have it switched that you can automatically switch it at a 5 time constant. Here's the current. When the cap is completely charged up, initially the current is the maximum. When the cap is completely charged up, the current goes down to 0. But at an instant you switch to position 2, the current will drop to, because the voltage has not changed yet. The voltage across the capacitors, at a moment you switch to position 2 for a discharging cycle, the voltage is still at E, but the current will automatically, instantly will change the direction, but it has the same magnitude because the voltage across the cap is still at E and the resistance R is still the same. So when discharging, the current is going to go down to E to the minus R. The negative current is just change the direction, but the same magnitude will go up to 0. When the charging comes in, it will jump again to whatever E or R is, and so forth. And the same thing for the voltage across the resistor will be exactly identical to this. So that shows you the charging and discharging diagram for the capacitive circuit. Now in this picture it shows the charging for and discharging. If you're going to use 8 kilo ohms and 4 microfarads in example 3 that we did, if I'm going to use that for this diagram, 8 kilo ohms and 4 microfarads, let's see what happens if I switch back and forth between position 1 and 2 after 5 time constant. Remember 5 time constant, the time constant was 32 milliseconds, 5 time constant was 160 milliseconds. So if I in position 1 and wait for 160 milliseconds, the cap is completely charged up, and then if I switch back to position 2, then you're going to discharge it, and that takes 10 times the time constant, 5 time constant, so maximum of 10 time constant, and so forth. So you do exactly what happens in terms of the time constant, but charging and a discharging cycle. Here shows the plotting of V sub C and I sub Z versus the time constant when A is equal to 32 milliseconds. Okay, the same picture that we had before. But now what happens if I change the time constant? So remember the time constant, to change it, to reduce it by a factor of 4, I can replace either R by a factor of 4 or replace C, or vice versa. Your product of the two variables, you can adjust them such that the time constant now is 8 milliseconds. Now let's see what happens. This is with 32 milliseconds, this is 8 milliseconds. You can see it charged a lot quicker and discharged a lot faster. So you're charging and discharging. Every time you're switching on your windshield wiper on your vehicles to change the speed of it, actually what you're really doing, you're switching it a different capacitance value, you're changing the time constant, you're charging and discharging a lot quicker. So everything will stay the same, the waveform, but you're just going to reduce it, reduce the number of, reduce in seconds the charging and discharging cycle. Now here it is. If a constant, if R stay fixed, and you're going to vary the C, the larger the value of C is, the larger the time constant. So it's going to take longer for a capacitor to charge up. Of course, that makes sense. If you have a larger capacitance, then you need to accumulate more charges. So it's going to take longer for the voltage to build up. As you get a smaller value for the fixed value, a smaller value of C for the fixed value of resistance, the time constant is smaller, so it takes a little bit shorter time to actually charge up the capacitor. Should be clear. Let's look at an example. It says for the circuit shown, find the mathematical expression for the transient behavior for the voltage across the cap, V sub C, and the current through it. If the capacitor was initially uncharged and the switch was thrown to position 1 at t is equal to 0 seconds. So cap is completely discharged. You come in, you have this hooked up in a lab at time t is equal to 0, you switch to position 1. Part B of the problem says find mathematical expression for the voltage C and the current I sub C if the cap is switched to position 2 at 10 milliseconds. So in order to find out exactly what's happening, you need to calculate the time constant. So first you want to calculate the time constant, which is equal to R1. If you look at the circuit, you're charging it up to R1 and discharging it through R2. So during the discharge cycle, the time constant is going to change. So be R1 times C. R1 is 20 kilo ohms times 0.05 microfarads. Everything has to be in there. It gives you 1 millisecond. So V sub C then is equal to E to the minus T over tau, which is 12 times the quantity E 1 minus E to the T divided by 1 milliseconds. For the current is E divided by R1, E to the minus T over tau. That gives you 0.6 milliamps, E to the minus T divided by 1 milliseconds. So that's pretty straightforward. Part B says, what is it, determine the mathematical expression if you move the switch from position 1 to position 2 at T is equal to 10 milliseconds, assuming the leakage current is 0. So I'm assuming that with the leakage current is 0, that means the cap is going to hold a charge, whatever it is, at 10 milliseconds, which we need to calculate. But if you remember, the time constant is 1 millisecond, so after 10 milliseconds, that's already 10 times the time constant. So the cap is completely charged up to the full value of 12 volts. So B, the V sub C is equal to 12 volts. Cap is completely charged up. The current would be 0. You have this cycle right here, a 5 time constant. And 10 milliseconds right here, so the cap completely charged up. It's going to hold a charge. There's no leakage current, so the current would be 0. So that part is fairly simple, part B of the problem. Part C, now it says find the mathematical expression for the voltage V sub C and the current I if the cap is, if the switch is moved from position to position 3 at T is equal to 20 milliseconds. So if you move to 20 milliseconds, and if you look at the circuit, then the cap is charged up to 12 volts, and then you switch to position 3. That means you're going to cap is going to discharge. The current is going to change the direction. It's going to discharge through 20K plus 10K. So the time constant would be different. We're going to call that tau prime. R1 plus R2 times C. That's 30 plus 20 plus 10 is 30 times 0.05. So it gives you 1.5 milliseconds compared to 1 millisecond. So the discharging would be 50% longer compared to the charging. So the voltage now, this is the equation for the discharging. You're at this point, it's going to go down e to the minus t over tau prime, which is 12 e to the minus t divided by 1.5. There's a typo in here. Please make that 20 milliseconds, because the problem is asking what happens if you switch at t is equal to 20 milliseconds, not 10 milliseconds. But it doesn't really matter. The waveform will still be the same, but that should be 10 milliseconds. I'm sorry, 20 milliseconds, because at 10 milliseconds is already a full charge, but you don't switch to position 3 at 10 milliseconds. The problem is asking you to switch at 20 milliseconds. So that should be 20 milliseconds. It takes 5 time constant, so 5 times 1.5 times the time constant, which is 5 times 1.5, that's give you 7.5 milliseconds. So add that to 20 milliseconds, it should be 32.5 milliseconds. It's not 22. So instead of 10, that should be 20 milliseconds, that should be 25 milliseconds, that should be 32.5 milliseconds. We get a 20 and then a 5 time constant of that, it gives you 32.5 milliseconds. And the same thing with the current. So the voltage then would be 12. You charge up to 12, and it's going to discharge with a time constant of 1.5 milliseconds. The current I now, it will change the direction. You've got to make sure it's negative. E divided by R1 plus R2, which is 12 divided by 30K instead of 0.6 millisecond. Now it's reduced to 0.4 milliamps. And then we'll go down to 0. I'm sorry, that should be 1.5 milliseconds. For the charging, once you calculate a time constant, all the voltage in the current, as I said before, they will charge and discharge with the same time constant. If the time constant is now 1.5, that's a typo there again. That should be 1.5 milliseconds. And then part D of the problem says plot the waveform for part A through C. So you already done that. Let's look at another example. It says in a capacitor network discharge phase, now you have a current source. At time t is equal to 0, you switch to position 1, and you want to calculate the voltage across the cap and the current through it, just like the previous problem. But the first thing you want to do is to use that equation, you must convert this from a current source to the voltage source. So 4 milliamps times 5K, that gives you 20 volts. And the 5K will be connected in series with it. So almost identical to the previous problems. Then you calculate the time constant, but you have to be careful when you're charging. You still have this 3 kilo ohms in a circuit, so you're charging to 5K and 3K, which is 8K, times 10 microfarad. That gives you 80 milliseconds time constant. Just plug it into the equation. 20 is a voltage, e to the minus t over tau, and that's 20 e to the minus t divided by 80 milliseconds for the time constant. Now it says find the mathematical expression for the voltage if you switch to position 2 after one time constant. Here's the difference. The cap is not completely charged up to the full charge, 20 volts, but you're switching after one time constant, which is e to the minus 80 divided by 80. So it gives you e to the minus 1. That gives you 63% of the final. So if the switch of position network appears as shown in this figure, so switch to position 2, then you got 1K, you kicking that one in, 1K now to 3K, so the time constant would be different. But at that point, to see how much voltage you have, so you plug it in one time constant, which is e to the minus 1, and that's 63% of 20 volts, just give you 12.64. 1 e to the minus 1 is actually 0.632, and that gives you 12.64. So at one time constant, the voltage across the cap is built up to 12.64, and then at that point you're switching to position 2. The capacitor is going to discharge with that initial voltage. So tau now would be equal to 1K plus 3K. It's 4K, so it's 40 milliseconds compared to 80 milliseconds. So the cap is going to charge up, it would be discharging with E times e to the minus t over tau prime, which is 12.64 e to the minus t divided by 40 milliseconds. And then it says plot the resulting waveform for the voltage as determined in part A to C. Repeat it, the same thing for the current I sub C. So for the current, this is what happened initially. The voltage was 20 volts, but the resistance, the time constant was 5 and 3, it was 8 kilo ohms. So the waveform for the current during the discharge would be, I'm sorry, that should be positive. During the charging is positive, that's 2.5, that's a typo. So it should be 2.5 milliamps e to the minus t over 80 milliseconds. So during the charging, it gives you 2.5 milli at the maximum, but it's not fully discharged at one time constant. You plug it in, t is equal to one time constant in here, which is 80 milliseconds. That gives you 2.5, which is about 36% one time constant. That gives you 0.92 milliamps. So at 0.92 milliamps, you're switching to position 2. Now the current will move to, you have, remember we had 12.64 voltage here at position 1. When you switch into position 2, that voltage divided by 1K plus 3K, which is R2 plus R3. That's the V sub I, that's initial voltage, which is this voltage right here, 12.64. Now acts like an initial voltage for the next cycle. So at that point, when you're switching to position 2, the voltage is built up to 12.64. Now that change of direction is going to discharge to R2 and R3. So to calculate the current instantly at that point would be negative current minus V sub I divided by R2 plus R3. And that gives you minus 3.16 milliamp with a time constant of 40 milliseconds. So the current at 0.92, when you switch to position 2, it will drop down to 3.16 negative, and after that it's going to build up and it will go back to 0 again when the cap is completely discharged. Please make a note of that. Should be a positive current. Now, initial conditions, the voltage across the capacitor at that instance is called the initial value. So if you have some kind of initial voltage, the cap is not completely discharged, either the leakage current is extremely small or you just charge it up and left it in there. That's called initial conditions, which is shown in this picture. That's the voltage. Now, if you're charging up the voltage, then of course it's going to go to a transient response and reach a steady state region, and we're going to call that a V final. So you have V initial and the V final. So if I look at the voltage during transient, we already have the equation is E1 e to the minus t over tau, where E is equal to the difference between a final and initial value. But the voltage in time for the capacitor is equal to initial value plus the transient that it builds up. So if I plug that into the equation, V sub C of t then is equal to V sub I for the initial value, and plus the transient, which is this equation right here, but I'm going to substitute V sub F minus V sub I to give you this equation. The book does a slightly different, but it's the same thing. Now if I multiply this out, V sub F times 1, V sub F minus e to the minus t over tau, minus V sub I minus minus to give you plus V sub I e to the minus t over tau. If you notice, V sub I plus and V sub I minus will cancel out. You're left with V sub F minus V sub F e to the minus tau, and then plus e to the minus t over tau. I'm going to factor out e to the minus t over tau between these two terms, so we'll be left with V sub F plus V sub I minus V sub F times the quantity e to the minus t over tau. This is the equation we're going to use. This is more universal equations. You can pretty much solve for the voltage across the capacitor, the DC voltage. We haven't talked about AC in this course. So this equation is valid for any type of a voltage across the capacitor, DC voltage, and with one capacitor, one storage elements. You can use the same equation for all the currents and the voltage. I could have said that a V sub I of t, I sub C of t is equal to I of F plus I of initial minus I of final e to the minus t over tau. So the same equation can be applied both to the voltages and all the currents in the same circuit. Let's look at an example. Say the capacitor has initial voltage of 4 volts. Again, it's indicated here that when they say plus or minus 4 volts in the cap, that means you have an initial voltage of 4 volts. It says find the mathematical expression for the voltage across the capacitor once the switch is closed. When the switch is closed, the cap is going to charge up between 2.2 and 1.2 K. So the time constant would be 1.2 plus 2.2 K times the cap, which is 3.3. If you calculate that, it gives you 11.22 milliseconds. We just write the equation. V sub C of t is equal to V of F plus V sub I minus V of F e to the minus t over tau. The final value, when the cap is completely charged over 4, so you're going to reach 24 volts. So it's 24. V sub I is 4 minus 24 e to the minus t divided by 11.22 milliseconds. 4 minus 24, it gives you minus 20. So that's the equation for the voltage. Now you can do it for the current. When the switch is closed, the cap has 4 volts. So the total voltage across the resistors is 24 minus 4 volts, which is 20 volts divided by the sum of those two. So the initial value, which is the maximum value for the current, is equal to E minus V sub C divided by R1 plus R2, and V sub C is actually V sub I initial. So at that point, initially, so at t is equal to 0, which is 4, so it'll be 24 minus 4 divided by 3.3 K. That gives you 5.88 milliamps. And you don't need to calculate the time constant. Again, as I said, all the voltage and current will be the same. Now at the final value, I've got to use the same equation here. The final value, I sub final is 0, I sub initial is 5.88, and I of final is 0. So you get the same equations. So that's the equation for the voltage. So how the voltage is going to look like is a constant 4 volts until t equals to 0. and then it's going to build up, go up to 24 volts after 56.1 millisecond, which is 5 times 11.22. And same thing for the current. It'll start out with 5.88 milliamps. It'll go down to 0 after 5 time constant. All right, we'll stop here and we'll continue that next time. Thank you.